Ladies and gents, today we will talk about Lesson 1, Generating Equivalent Expressions. And we will begin with Module 3. First, before we start our lesson, we need to discuss the vocabulary that is in this. The first one, a variable. Well, a variable is a symbol that represents a number or a set of numbers. We are going to more commonly see alphabet letters. In geometry, you will see Greek symbols such as beta, rho, omega, alpha, theta, and many more. However, for this class, we are going to focus on alphabetical letters that will be used as variables. A term. A term is a singular value in an expression. So it can be a number, just a number. It could be just a variable. It could be a number multiplied to a variable. Or it can be variables multiplied to each other. Or it can be a variable divided by a number. For example, if we had the expression 3x plus 2, 3x is a term. 2 is a term. So here we have two terms. The first term, 3x. The second term is 2. Next, we have a numerical expression. A numerical expression, it's an expression that uses numbers. So it can be a combination of sums, differences, products, or division of numbers. So an example, 4 plus 5. Next, we have an expression, or what I like to call more so like an algebraic expression. It has both numerical and or variables included in it. So an example would be 4 plus w. An equivalent expression, 4 plus 5 is the same as 5 plus 4. W plus z is the same as z plus w. So it's very similar to the concept of the commutative property. The coefficient of the term, the number used to multiply a variable. For instance, 4x. 4 is the coefficient. wxy, 1 is the coefficient. If there is never a number in front of the variables, and no minus sign or negative sign, then the coefficient is 1. And why is that? Because anything times 1 is itself. So 1 is the coefficient for wxy. Let's begin with the opening exercise. So for the opening exercise, we have pictures of triangles and quadrilaterals. And for this exercise, we're going to let T represent the number of triangles and let Q represent the number of quadrilaterals. Yes, we have 4 triangles and 2 quadrilaterals. However, we want to use variables in this simple case to start off with expressions. So we want to write an expression using T and Q that represents the total number of sides. And then we're going to explain what the terms in the expression represent. So, first, look at the triangles. How many sides are on a triangle? 3. So, since we have T triangles, we're going to multiply T by 3. We have 2 quadrilaterals. Okay, well, each quadrilateral has 4 sides, so we're going to take 4 and multiply it to Q for Q quadrilaterals. So our expression, to find the total number of sides, we would add those two terms together, 3t plus 4q. And what that simply means is that triangles have 3 sides, so we have 3 sides for each triangle, so this is represented by 3t. Same with the quadrilaterals, they have 4 sides, so this is represented by 4q. Let's look at part B. Let's say you and your partner Joey, you have the same number of triangles and quadrilaterals. Write an expression that represents the total number of sides that you and your partner have. And if possible, write more than one expression to represent the total. Well, here's the first expression. First, we could just add both you and your partner Joey's together. Both of you have 3t and 4q. So we could just add 3t plus 4q plus 3t plus 4q. That's the first way we could write it. Another way, since there's two of us, we both have the same thing, we could multiply it by 2. 2 times the quantity, 3t plus 4q. And lastly, another way that we could write this expression is in its most basic, simplest form, 6t plus 8q. Let's continue on to part C. For part C, each person in the class contains the same number of triangles and quadrilaterals. There are a total of 22 students in our class, so we're going to write an expression that represents the total for the entire class. Well, if each one of us has 3t plus 4q, we can multiply that by 22. So the expression is 22 times the quantity, 3t plus 4q. Let's continue on to part D. For part D, use the given values of t and q in your expression from part A to determine the total number of sides for 4 triangles and 2 quadrilaterals. Okay, so the given values for t and q from part A, we have the picture of the 4 triangles and the 2 quadrilaterals. So we're going to plug those values in to the expression from part A. Well, our expression from part A was 3t plus 4q, so we're going to plug in 4 for t, because we have 4 triangles, and 2 for q, because we have 2 quadrilaterals. So we have 3 times 4, which is 12, 4 times 2, which is 8. We add our sum together and get 20. What does 20 represent? The total number of sides. Let's continue on to part E. We're going to use the same values for t and q in our expression from part B to determine the number of sides that should be contained between ourselves and our partner Joey. Now, there are 3 different variations of how we could solve this problem using our expression. Variation 1, we could write out 2 times the quantity 3t plus 4q. Variation 2, we could just add all of both ours and our partners together. Variation 3, we could write it as 6t plus 8q. Our next step for any of these variations, we would plug in our values, 4 for t, 2 for q for each one. We would then simplify, and we would completely simplify our answer. Variation 3 is going to get there very, very quickly. We would find that variation 3, our answer is 40. Variation 2 and variation 1 should have the exact same answer. They're just a different way of solving the problem. So our final answer is 40. What's that mean? It means there's a total number of sides between us and our partner Joey would be 40 sides. Let's continue on to part F. For part F, use the same values for t and q in your expression from part C to determine the number of sides that the entire class of 22 students has. Well, we're going to have 3 variations. Variation 1, we multiply the quantity by 22. Variation 2, add 3t plus 4q to itself 22 times. And variation 3, 66t plus 88q. If we plug in our numbers, 4 goes in for t, 2 goes in for q, and we begin simplifying. We continue to simplify the problem. Variation 3 once again is going to get there very quickly. Variation 1 is not too far behind. Variation 2 will involve a lot more writing. But in this writing we want to have that plus ... and that's for variation 2. Do we have to write it this way? No. We would not have to solve our problem this way. We could use variation 1. We could use variation 3. This is just showing and demonstrating different ways that we could solve this problem. And finally, simplifying our answer, we get 440. And we should get this for every single one. So 440 is our final answer for all three variations. 440 means we have a total of 440 sides for the entire class size of 22 students. Let's look at part G. For part G, what do we notice about the various expressions in parts E and F? Well, first, the expressions are all equivalent in part E. The expressions are all equivalent in part F. There appears to be several relationships happening with the commutative, associative, and distributive properties. That's what we want to have seen. Looking at those answers, those different variations, there's a lot of relationships that are happening between the commutative, associative, and distributive properties. Let's begin with example 1. Example 1, any order, any grouping. We have the following problem. We want to rewrite the two expressions by combining like terms. Well, first, 5x plus 3x, that's the same as writing out x 5 times, added to itself 5 times. 3x, it's the same as adding x to itself 3 times. So when we combine 5x and 3x, we get a total of 8x. These are like terms. 5x and 3x both share an x. They have the same variable, and we can combine them because they are similar. And we get a total of 8x. For the 5 minus 3x, similar process. We can write out 5x's and then take away 3 of them. Our final answer is 2x. Because both terms have the common factor of x, we can use the distributive property to create an equivalent expression. So for instance, for 5x plus 3x, we can pull a 5 and a 3 into its own little quantity. Because both terms have an x, we can pull that x out from 5x and 3x. Take the x away from both of them. So it's like the distributive property, except in reverse. What common factor do both of these terms share? They both share an x. We can pull the x out and group the 5 and 3 together. Same with 5x minus 3x. They both share an x. Pull the x out, group the 5 and the 3 together. 5 minus 3 becomes 2. We simplified it, so now we have 2x. Looking at part I, find the sum of and 5x. Well, first, write the original expression. We have 2x plus 1, that's our first expression, plus 5x. Using the associative property, we can put our grouping symbols around 1 and 5x. Use the commutative property of addition, reverse the order. Once again, associative property of addition, group the 2x and the 5x. These are like terms. We can combine them. So we combine the 2x and the 5x to get 7x, finally plus 1. There's lots of properties that are happening here. But over time, do we have to list every single property in every single step that we're doing? No. For now we are, to gain a better understanding of how we're doing this process. But once you are conquering this with a firm understanding, these steps can be combined into one. Find the sum of negative 3a plus 2 and 5a minus 3. We're going to do a very similar process. Write the original expression. We're adding these together. We can rewrite this as adding the opposite, so additive inverse. So negative 3 plus 2 plus 5a plus a negative 3. Any order, any grouping, we want to put the numbers in the best order we can that will help us combine like terms very easily and very quickly. So negative 3a plus 5a and 2 plus a negative 3. The negative 3a and 5a make 2a. 2 plus a negative 3 becomes negative 1. So this, our final answer, is 2a minus 1. That is our final answer. Example 2. Once again, any order, any grouping, find the product of 2x and 3. Well, if we're multiplying 2x times 3, that's like saying 2x added to itself 3 times. We would get 6x. If we were looking at the product, we could use associative property of multiplication. Instead of having the grouping around 2x, we can group it around x and 3. Use the commutative property of multiplication to rearrange them, any order. And then next, we can actually multiply. Do 2 times 3 to get 6 and have 6x. Once again, we're listing the properties, going into great detail, but with a firm understanding, we can combine these steps into one. Example 3. Let's do parts A, B, and C. For part A, we have 3 times 2x. For part B, we have 4 times 5. That quantity is multiplied to y. For part C, we have 4 times 2 times z. Let's check our answers. Well, first, for part A, our main focus is 3 times 2. For part B, 4 times 5, it was already grouped. That becomes 20. We have 20y. So for part B, we're done. 20y is our answer. For part C, we want to focus our attention on 4 times 2. So for parts A and C, A, 3 times 2 is 6, so 6x is our answer. And then for C, 4 times 2 is 8, 8z is our answer. Let's move on to part D. For part D, we have 3 times the quantity, 2x, plus 4y times 5. Notice the 4y times 5, that's in a different order. That's okay. Because of the commutative property of multiplication, we can rearrange those. Let's take a look. So we have 3 times 2x plus 4y times 5. So 3 times 2x, that's the same as writing 2x, adding it to itself 3 times. And then 4y multiplied by 5, we can add 4y to itself 5 times. So like in this diagram, 2x added to itself 3 times, that's 6x. Well, that's the same as 3 times 2. 4y added to itself 5 times. That's the same as 4 times 5, which is 20. So our final solution, we get 6x plus 20y. Let's move on to part E. For part E, we have 3 times 2x plus 4y times 5 plus 4 times 2 times z. Similar to the diagram above, let's take a look at how this would look. Well, the 2x multiplied by 3, it's like adding 2x to itself 3 times. Same with the 4y, adding it to itself 5 times. And then with the z, adding it to itself 8 times, because 4 times 2 is 8. So adding 8 z's all together. If we simplify this, our final answer is 6x plus 20y plus 8z. We cannot combine unlike terms. We can only combine like terms. So here what we're doing is we're multiplying 3 times 2, you get 6x. We cannot simplify that any further. We cannot combine that with anything. 4 times y times 5, 4 times 5 is 20, so we have 20 times y. We cannot combine that with anything else. That term is completely simplified. 4 times 2 times z, that becomes 8z. We cannot combine that with anything else. Example 3. Part F. Alexander says that 3x plus 4y is equivalent to 3 times 4 plus x times y because of any order, any grouping. Is he correct? Why or why not? Well, first, he is not. He is not correct. Alexander is incorrect. They are not equivalent. Let's do an example. Let's say that x equals -2, y equals -3. If we do this and plug it into both expressions side by side, we will see how they are not equivalent. So first, we have 3x plus 4y, and then on the other side we had 3 times 4 plus x times y. And these are the two expressions we're going to plug in the values for x and y. We're going to simplify them and see if they are equivalent or not. Because our goal here is we wanted to see if he was incorrect. We wanted to come up with a counter example. something that would show that he is incorrect. Okay, we plug in -2 for x, -3 for y. We begin simplifying. On the left side, we have 3 times a -2 plus 4 times a -3. This simplifies to -6 plus a -12, which that will simplify to a -18. On the right side, we had 3 times 4, that's 12. We had a -2 times a -3, that becomes a +6. 12 plus 6 is +18. -18 does not equal 18. Therefore, the expressions cannot be equivalent. All it takes is one counterexample to make it not equivalent. This concludes lesson 1. Thank you so much for joining me. If you have any questions, please bring them in to the next class.